This is lecture 10 of Category Theory 2023, an NITheCS SATACS course. We will start off with a suggestion from Alexandre, which is to talk about free objects and comma categories. So a very important construction in mathematics that arises in various different areas of mathematics is the construction of a free structure of a certain type. Now, in fact, this construction is a relative construction because when we talk about something to be free, it's always relative to another structure of a different type. So free structure of a given type relative to another type of structure. But moreover, these two structures need to be already related somehow before we can talk about one being free relative to another. And the relationship of these two types of structures will be given by a functor. So let's work on an example. I guess the most easy example to work with would be if we choose for the first type monoids, so we take the category of monoids, and for the second type we take sets. Now the functor we have from monoids to sets that we want to consider in this case is the expected one. So if we take a monoid which consists of a set, a binary operation, and an identity element, we want to forget the operation and the identity element. We just want to keep the set. This is called the underlying set of the monoid. So if this is a monoid, M will be called the underlying set of the monoid. And we can denote this functor by U, where U comes from the word underlying. So in general, the idea is that these two types of structure of the first type here, of the given type, and of the other type relative to which we are going to be considering the notion of freeness, these two types of structure are such that the first one kind of builds on the second one. So there is some basic structure, and then in this case it's a set, and then a monoid is something that's a set enriched further with additional data. In this case, it's a binary operation and an identity element. And the forgetful functor, this is how U is called, because it forgets piece of the structure. U is called forgetful functor. So that what forgetful functor does, it removes the added information. Okay, now the idea of free structure is to basically go backwards here. So we want to be able to, if at all possible, reverse this process of forgetting the structure. We want to begin with a set and put over it a monoid structure. But the problem is that there are many ways to do that. And so these different monoids over the same set will not be isomorphic. So the functor u doesn't actually have an inverse. It has, though, an adjoint. And this notion of adjoint is the same notion of adjoint that came up in our discussion about exponentiation. But we are not going to yet think about the general notion of adjoint. We're going to explore this idea in the specific example, and then if we have time, then generalize from there. So intuitively, if I've got a set M, or rather let me call it X, because now this set comes without any predetermined monoid structure. If I've got a set X, what I want is to turn X into a monoid. So you want to start multiplying elements of X with each other, right? But you don't want to force this multiplication, because if you force it one way, then another way of multiplying things will be missed out. So you kind of want to start multiplying elements of X with each other in the most free possible way, that you do not give priority to one monoid or another. And then you basically will be moving out from your set X. So the product of elements of X should no longer reside in X, because if they do, then you're forcing some specific type of monoid structure on X. And as we said, there could be several. So the monoid that we will get out of X will have its underlying set different from X, but there will be an insertion map from X to that underlying set. We call this map eta. I need to also draw the monoid here. And notice that the map eta is a map from X to the underlying set of the monoid, because it wouldn't make sense to talk about a map from X to the monoid itself, since the monoid and X, they live in different categories. This lives in the category of monoids, and this lives in the category of sets. So basically, our M will turn out to be the category of words over X. Where the multiplication is concatenation of words, and the identity element is the empty word. Is this something that's familiar to you, Alexander?
Yep, I know it from groups, actually.
In groups, this works slightly differently. It's kind of easier for monoids, because in groups we also want inverses.
Yep.
Now the fact that this idea that we pointed out that we wanted there to be freedom in the way we multiply things, and we really allowed full freedom in the sense that we're basically declaring that any kind of term like X times Y times Z is its own independent element. It will never be equal to, let's say, Y times X times Z, because as a sequence of letters, these two are different things. So it's, in a sense, we're giving this monoid structure to have completely full freedom from the point of view of our earlier intuition. And those of you who are familiar with vector spaces, this corresponds to building a vector space out of a basis, where again you take linear combinations of your basis vectors, and there is full freedom as much as the vector space axioms allow, of course. Also here, we definitely do not want this to be different from this, because monoid axioms force them to be the same. So that's why we don't have brackets, because since these two terms are the same, or any arrangement of brackets in a longer term will always give the same element, then we can just write this element without the brackets. So this idea that words is a kind of free monoid over X can be expressed as a property of the of this object, of this monoid, relative to the forgetful functor. Before stating it for a general functor, in this specific case, what we will observe is that if I had another monoid n, maybe I'm going to call it m prime. If I had another monoid m prime, and I had a way to move from X to m prime, this would mean that the elements of X are now interpreted as elements of m prime, right? So let's say this function is f. For every x in X, we now have a corresponding value f of X, which is in m prime. Of course, this function f doesn't have to be injective. It could also be that several elements map to the same element. And then things like x, y, z will obtain some kind of value in m prime. I can now read x, y, z as fx, fy, fz, where we use the multiplication of m prime for putting these three things together. So this is dot prime. But with this, we're of course saying that there will actually be a map from m to m prime. And this map from m to m prime, in fact, comes out as a monoid homomorphism called f bar, from the monoid of words to this m prime monoid. It's not difficult to see that it will be homomorphism, because the operation in the monoid of words is just putting words together. So if I, for example, if I have another term, let's say st, that maps to f of s dot f of t, then x, y, z times st in the monoid of words, which is the same as just the word x, y, z, st, will, according to this rule of mapping, it will map to fx, fy, fz, fs, ft, evaluated in the monoid m prime. But that, of course, is the same as grouping the first three together and then multiplying that by grouping the second two together, just by associativity of the operation n m prime. And so as a general rule, we get that if I've got words w1 and w2, I multiply them, and then I evaluate by applying this f bar map, right? I apply f bar to this word, is the same as f bar applied to word 1 times f bar applied to word 2. And here on our example, this is this was w1, this is w2, and here I've got f bar applied to w1, here I've got f bar applied to w2, whereas this expression here is f bar applied to w1 times w2. And we see that they're indeed the same. Also, the identity element will be preserved. Remember, the identity element here is the empty word, and that means taking empty product inside this monoid. By convention, empty product is the identity element of the monoid, so it's basically preserved by convention. Does this make sense so far for both of you, Lian and Alexander?
Yeah.
Yes, sir.
Wonderful. So we've got this F bar, and of course, for the F bar, the following triangle commutes. F bar composed with eta x equals F. And why is that? Well, remember F bar evaluates words, and eta x will create words out of a single letter, and then evaluating is just applying F to it. And so that's what this equality says. So an example here, F bar composed with eta x of x will be F bar of x, which is a single letter word, is F of x. Now the F bar is not some homomorphism that exists from there to there, which makes this triangle commutative. It's not just that. It also makes it's also the unique homomorphism that will make such a triangle commutative. So there is in fact unique F bar for which this triangle commutes. How do we see that it's unique? Well, basically the definition of F bar forces us it to be unique because, again, on an example, if I try to apply F bar to a word, let's say x1 up to xn, let me put it as a sequence. Because F bar needs to be a homomorphism, this value needs to equal to F bar applied to x1 times F bar applied to x2 times so on times F bar applied to xn. But then each of these xi's will be equal to, would you like to help me, Alexander? What do I do next? I'm trying to derive the formula for F bar to get convinced that F bar must be defined the way we set it to be defined, hence making it unique.
But I don't really see it.
Well, so what is xi as a single letter word? Xi as a single letter word is nothing other than eta x applied to xi. Do you agree with that?
Yeah.
So we can rewrite each of the x's this way. But then, if I want triangle 1 to commute, then each of these terms will have to be equal to f of that x. Do you agree with that as well?
Yes, from the triangle, I see.
Yes. And there we go. We now have a unique value that this could have. It must be equal to this if the triangle commutes. Are you happy with that, Lian?
Yes, sir.
Okay. So if you have any questions at any point, please do interrupt me. Okay, so we've shown that this F bar doesn't only exist, but it's actually unique. So we've established some property of the pair, the monoid here, and the eta, which now I want to formalize this property. And if you recall the definition of initial object, this looks very familiar to the definition of initial object, which says that there must be a unique arrow going to any other object from a given one. It feels like this whole data is a kind of initial object in the sense that it has a unique arrow going into another similar data. And that actually will be the formalization. So, but now I need to introduce this category of such data in which the thing will be an initial object, and that's the concept of comma category. So if I've got two categories, we had monoids and sets, but let me abstract it away from there now. So let's say we've got two categories, M and S, and a functor between them, let's say U. From this functor, we construct another category, which is called the comma category because it's written with a comma. And specifically, it's written the following way. However, it was written with a comma only in traditional notation of Bill Lovier, who introduced this idea first. Later, it was agreed that it will be written in a slightly different way. So instead of comma, we've got an arrow. And the reason for this is that this notation is a bit more suggestive. The arrow here represents this eta x. So it kind of tells you that you want arrows from S to U. But what does it mean to have an arrow from a category to a functor? That doesn't seem to make sense, right? So instead it will be, but we want this whole thing itself to be a category. So its objects will be such arrows. So let's take an object of S, namely X. But now, what does it mean to take an object of U? That doesn't make sense either. So let's rather take an object of M and evaluate U at that object. And then we could consider an arrow. Maybe I don't want to call it U, but let me call it F. And let me actually call this thing, what did I call it before? M prime. Okay, then I'm going to call it M prime here as well. Okay, so these will be the objects of the comma category. So these are objects. Of this comma category. In other words, I can think of them as diagrams, but I can also think of them as ordered pairs. The objects are ordered pairs. Are they pairs or triples? They are rather ordered triples. Yeah, actually, I want to consider a special case of this construction where S will be replaced with just a fixed object.
So is it like some object from our category M? Or
X is an object from S.
Okay.
So we've now fixed an object in S. The most general definition of comma category involves two functors, U and V. And in this case, we can think of the functor V being a functor from a singleton category, which specifies the object X. So X is a fixed object, and U is a functor. And we're defining this new category here, where we're saying that objects are ordered pairs. So because X is fixed, I don't have to worry about X anymore. There are ordered pairs consisting of an object M prime of M and a morphism F from my fixed object X to U of M prime, which I will just write as M prime comma F. So these are the objects of the comma category. What about morphisms? So a morphism let's call this morphism U. Maybe I will not call it U, maybe I'll call it H. From, let's say, M, let me not call this M prime to make the notation more symmetric. MF to M prime F prime morphism is, and maybe you can help me here to define what a morphism should be after I draw a diagram that will be suggestive to what it should be. So
it should be some morphism from M to M prime, such that
not correct, not correct. You're close, but not quite. So we've got this. Remember, F and F prime are morphisms from UM to UM prime. And M and M prime themselves live in the category M. And now you were saying it should be a morphism here, making the triangle commutative, right?
right.
And what we actually want is
a morphism from M to M prime.
That's right, yeah.
Oh.
Remember, that's what we had here. This F bar was a unique homomorphism, not a unique function from M to M prime. There'll be many functions from M to M prime making this triangle commutative, but only one that's actually homomorphism from the free monoid to that other monoid. So is a morphism from M to M prime in the category M, such that this triangle with the U applied to this morphism is commutative. Can we compose morphisms? We still need to define composition, right? Otherwise, we don't yet get a category until we specify what composition is. Well, composition is not difficult to see what it will be, right? If I've got two such things, one following the other, I've got my H and H prime. And let me also draw the corresponding triangle below here. So UM prime, and UM double prime. Got my X here. There are three objects given by F, F prime, F double prime, together with the M, M prime, and M double prime. And now I know that these two triangles commute. UH is here, UH prime is here. So I want now to be able to compose these H and H prime, and of course I'm going to take the composite to be just the composite, the usual composite in M. So this will be just H prime composed with H in M. But then how do I know that the triangle still commutes for that composite? So let me draw that in. How do I know that now if I do U of H prime composed with H, how do I know that I still get U of that thing composed with F equal F double prime? That's the bigger triangle I need to commute in order for this thing to be morphism from this object, well, rather this object to that object, right? So Lian, would you like to suggest how, explain how do we know that that bigger triangle will commute?
I'm not too sure, sir.
Okay. So I know that these two triangles commute, right? The smaller ones. Because H is a morphism, the triangle number 1 commutes. Because H prime is a morphism, triangle number 2 commutes. Do you agree with that?
Yep.
But then it will make the bigger triangle commute, because what does it mean to commute? So if I go here and I go this way, it's the same as going that way and that way, which is the same as that, right? So this triangle certainly commutes, but now we actually want the other one. We want this triangle. But of course, this composite and that morphism are the same morphism because U is a functor. So this equals UH prime composed with UH composed with F. And then UH composed with F is F prime. So we get UH prime composed with F prime. And UH prime composed with F prime, because of this triangle now, is F double prime. Does that make sense, Lian?
I'm drowning in arrows a bit, sir, but I'll just go through it on my own in the background.
Okay. How about you, Alexander?
Yep, it's understandable.
Okay. So that's how composition will be defined. And we also want the composition to be associative, but that will be true because composition is associative in M. Since composition is defined the same way as in M, associativity in M will also give associativity here. And identity morphisms here will also be the ones that come from M. It's quite evident that the necessary triangle for the identity morphism will commute. So if I've got the same object, F and F, then I just take one M here, and then I apply U of that. Because U is a functor, it will be 1 of UM. And then this triangle will commute because of the fact that this is an identity morphism. So we use here functoriality of U along with the fact that M is a category. So we get a category, and this category is called comma category. Now, what is an initial object in this category? Well, going back to our initial diagram there, so you see here now, this thing is an object in that category, right? It's a monoid along with a morphism into U applied to that monoid. So this is one object. Now we're saying that for any such other data, but what is that other data? That's another object, right? M prime again is U applied to M prime dot prime 1 prime. There must exist a unique morphism from that monoid to that monoid, but that's exactly what a morphism, I mean, a unique morphism making this triangle commute, but that's exactly what a morphism is from this object to that object in the comma category. Is that clear, Alexander?
Yep, I see it.
So the initial object, but of course initial objects are unique up to isomorphism. Nevertheless, I'm going to call it the initial here. The initial object in the comma category when U is a forgetful functor, is called the free object. Well, you see, it's a bit misleading to talk about free object because it's not just object in, so it is an object inside the comma category. It's not just an object in M. It's important to keep in mind what the map eta is. And when such object exists for every x, we get a functor. And this is to be proved still. So for each x, so let me first draw the category M, the category X, wait, sorry, we had S here, and U. So I could take X and assign to it okay, first we need the notation for that initial object. So remember that initial object would have been, so let me draw that separately. So for every X, I've got the special object, I've got the special pair, M eta X, where this is initial in the comma category X comma U, right? And what I'm going to do now is I'm going to pick an object X and assign to it the M that comes from this initial pair. So let's call this something. Let's call this thing MX, M subscript X, like we call that one, eta X. Then I'm going to have MX here. So now I want to produce a functor going from a kind of inverse of U. It will not be an inverse, but it will be an adjoint rather. So I want to construct a functor this way. So I'm going to take an object in S and I'm going to map it to the object part of that pair, which is itself is an object in the comma category. But I want to get convinced this is a functor, so I need to know what to do if I have another object and a morphism. I need to know how to produce out of a morphism in S, let's call it small s, I need to know how to produce something here if it exists at all. So let's learn how to do that. So the fact that it's a functor, we will see now, which we will get convinced of below. Okay, so let's redraw this diagram, but this time with the eta also drawn inside it. So I'm going to take the same diagram where I want to produce possible arrow this way, and I'm going to shift this up a little bit and draw the eta x and eta y. So u of mx goes here, u of my goes here, and I've got here my eta x and I've got here my eta y. Can you now see how we could produce a morphism from mx to my? We're looking for something here that will be determined by s. What do you think should that thing be?
Well, I think I have it by definition, don't we?
Okay, but we apply definition to what exactly?
How to say it?
We know this thing is an initial object in the comma category, right? Means that for any other object, we'll have a unique arrow going to it. So I need to now specify another object in that comma category to which I will build a unique arrow. And remember that that other object will have to have the same x, because this x was fixed here where that thing was initial. I can't take this object because that does not live in the same comma category as this one does. This is only initial in x comma u. That one is initial in y comma u. So I don't yet get anything connecting these two objects because they don't even live in the same category. Any ideas, Leon, what to do? Well, first of all, before we answer this question, is everything clear thus far? Leon, are you comfortable with everything we discussed thus far? Do you want us to go back to something?
I'm I'm not too sure, sir. I'll have to go a bit
Okay,
slower after the lecture.
okay. Well, so yeah, sorry if I was a bit fast. So what about you, Alexander?
I think it's fine.
But then if it's fine, you should be able to quickly tell me what that thing should be. Otherwise, it means I'm going fast.
So mx and my live in the same category, don't say? So
Yes, they live in the category M. Yes.
so there must be, I think, some morphism between them.
Why?
Hmm.
So let me rewind here a little bit. So firstly, let's look at this comma category construction. Is it clear what the okay, maybe I'll chat with Leon. Leon, is it clear what the okay, first of all, is it clear what this is? Thing I'm marking in blue.
Just a functor, sir.
Yes, that's right. Wonderful. Now, is it clear what the objects in this comma category are?
Yes, sir.
So you see, when we say here that these are objects, this is a bit ambiguous because UM doesn't remember who M was. I actually want to remember M. That's why I wrote that they're actually pairs. I didn't quite realize that when I was writing this. So that it is IE should be more, in fact, more precisely. And visually, we can visualize these things, which are ordered pairs. We can visualize also, we can visualize them as X going up into UM, but we also want to write M separately because we want to keep track of M. We don't want just to know what is UM, we also want to know what M is. So you're happy with that?
Yes, sir.
Now let's visualize what morphisms are. So if this is an object, and I take another such object, F prime and M prime, keeping in mind that it's the same X, so I could actually redraw this. I could display the other object as an arrow going directly from this the left-hand side X and remove the right-hand side one. Maybe I actually want to do it a bit more symmetrically. So X is here, F is there, F prime is there. Then the morphism will be up there, H, but such that when I do UH, it makes the triangle commutative. So is that clear?
So it may not exist, right? Okay.
Yeah, doesn't have to exist. So in this diagram, the top part is happening inside category M. The bottom part is happening inside category S. And the object moves across both categories. So this is one object. This is another object. And now we're describing what a morphism from one object to another object is. Does that make sense, Liam?
Yes, sir.
So this is one object MF, and this is another object M prime F prime. Okay. Now composition is quite straightforward. We just compose the H's and the H primes and so on. And the fact that the composite will still be a morphism, namely the triangle will commute, that you can still check on your own. And now coming here, you see we've got this one object here. We've got another object, but now the problem is that these objects live in different comma categories. The first one lives in the comma category X, U. The second one lives in the comma category Y, U. What we want to do is to turn this process of creating mx out of x. I want to turn that process into a functor. So I want to be able to remember we had this isolation of the two categories. So the top part was happening in the category M. The bottom part is happening in the category S. And I want to view the process of generating mx out of x. I want to view that as a functor. So when I take x and I take this corresponding mx, which is now not just any object in the comma category, it's the initial object. It's the free object. So when I assign mx to x, now I assign my to y, I want that to be a functor, but to be a functor, I need to also decide how to create an arrow from mx to my if I've got an arrow from x to y. So is the statement of the problem clear, Lian?
Just to specify S.
So for every small s, I want to create something I will call ms, or rather m of s. So that this m is a functor. So that I get a functor here. So I'm looking for a functor from S to M whose values on objects are given by the free objects. So I've got an X, I take the comma category, and then I take in there initial object. And then look at the mx part, this m part of that initial object. That's my value of the functor m I'm trying to build at x. Is it better now?
Yeah.
Yes, sir.
So I'm trying to build this m as a functor. I only know how it works on objects. I'm trying to discover how could we make it work on morphisms. So now I need to solve this little problem here. How do I generate an arrow here from a given arrow s from x to y? And the only thing I know is that this thing is free object. In other words, it's the initial object in this comma category, and this thing here is initial object in that comma category. Any ideas?
So from the fact that UMX is like from its universality, so to say, so from here, for example, we have some how to say it, morphism from X to UMY, yeah?
That's right. Yeah, that's right.
So from universality, we must have some set from UMX, from MX to MY, such that U of Z makes the triangle commute.
That's right. That's right. Well done. So I did have originally an object in the comma category over y, but I could transport that into an object over comma category over x by composing s and eta y. So now I have the same diagram as I always had before. One object, second object. And now are both over x. Okay, and now I'm going to use the fact that this left-hand side one is an initial object. Because it's initial, there will be a unique morphism from here to there. That unique morphism means a unique morphism at the top there, which will be my f bar. such that the triangle commutes, and where the triangle is number one triangle here. So by the fact that mx eta x is free, we have a unique morphism f bar from mx to my such that u of f bar composed with eta x equals f, but our f by notation is just eta y composed with s. We then set m of s to be that unique morphism. So we define m of s to be f bar. Does that make sense, Lian?
Yes, sir. I think so.
Mm-hmm. Now we still need to confirm that this will give us a functor. I mean, M needs to preserve composition, right? So let's draw a picture for that. It also will have to preserve identity morphisms. Alexander, you're fine so far?
Yep, now I see it.
So first, let's look at the identity morphism scenario. So is M a functor? That's the question we want to answer. We now have M defined on objects and morphisms, so we want it to preserve composition and preserve identity morphism. So, but does M preserve identity morphisms?
So a question before we go. So from which category to which category M is a functor? From S to M? Or?
Yes.
Okay.
Yes. So we are forgetting about the etas. We are using them to construct values of M on morphisms, but we are forgetting them at the end. We will then recover them back because they will turn out to be natural transformations from the identity functor to the composite of the two functors, the M functor and the U functor, but that's still to come. So is M a functor? Does it preserve identity morphism? Does it preserve composition? So let's draw the pictures to clarify that. So preservation of identity morphisms means that if I've got an identity morphism from X to X, which is just the identity morphism of X, and then I take the corresponding M's, which will be given by this diagram. So the MX such that this thing is initial object in the common category, right? And then I take the same M, right? I apply M twice because I'm applying them to the same object. So I take MX here. This will be the same eta because it has to be the same thing because I'm applying M to the same object, X. I now want the unique arrow here that comes from this diagram. So remember how we defined M of S. So if this is my S, then I first compose the S with eta. But of course, when I compose S with eta, because S is identity morphism, that composite will be eta also, right? This will still be eta, right? And then here, the value of my functor is the unique morphism which makes this triangle commutative, right? And I know that such morphism exists and is unique. I just want to check whether actually it equals or not the identity morphism of mx. So I want preservation of identity morphism means that I want M of identity to be identity of M of x. So this thing here is identity of M of x, because this thing here is M of x, right? We write M of x as mx. Yeah. And I want to figure out now that this unique morphism here that exists, which is unique with the property that this triangle commutes, and notice that in this triangle I've got the same morphism here and there. I want to show that that morphism must actually be the identity of mx. Any ideas how to do that?
So identity morphism passes our conditions, and we know that there is nothing more.
Fantastic, fantastic. So this is a very typical argument in this kind of situations in category theory. I'm claiming that there is a unique morphism here. Well, I'm not claiming. I know that there is a unique morphism here making this triangle commutative, right? So if I have at least one such morphism, then that morphism must be the unique one. And indeed, if I take the identity morphism here, the identity morphism of mx, when I apply u to it, u of identity morphism will be an identity morphism because u is a functor. So it will be identity of u of mx. And because it's, so when this is an identity, of course, this triangle will commute because I've got eta x here and there. So now I know that identity morphism here fulfills the requirement that this triangle commutes, but I also know that there is unique such morphism that fulfills such requirement by initiality of this object, right? So since there is unique such, that unique is the one that we have at hand. Remember, we defined M of S as the unique thing here that makes that triangle commute, but that unique thing must be this one because there is only one, and this is one of them. And we know there is only one because this is an initial object. So that's how we can decide that MS must actually equal to identity of MX. Does that make sense, Lian?
It was a bit fast, sir.
Okay, let me go a bit slower because it's important to do things slowly because also other people will be watching these videos, and if you don't understand what I'm saying, if it's too fast for you, then it will be too fast for many other people as well. So let's do it a bit slowly. So it will help if I redraw the diagram because now we've got a lot of things going on in that one. So let me draw it on the right hand side. So I've got identity morphism here, and I've got my UMX, eta x, eta x. I've got mx here. Now, do you agree or not with the following statement? That if I take the identity morphism of mx, then I apply u functor to it. Do you agree that this triangle here will commute? And the reason why it will commute is because u being a functor, u of identity is the same as identity of u. But
Yes, sir.
okay. Now we know that if I take the identity morphism, I apply u to it, the triangle commutes. But remember, there can only be one such morphism here that makes it this triangle commute, because this object is initial object in the comma category. Do you agree with that?
Yes, sir.
So then this is the unique morphism that makes this triangle commute. But by definition, that means that this is M of my S. Are you fine with that or not?
Yes, sir. I'm fine with
Yeah.
that.
Yeah, because that's how we define M, right? We said that M of S is the unique morphism that makes the triangle commutative. Okay, so you're also fine with this, right, Alexander? I mean, you came up with the argument, so I expect that you'll be fine.
Yes, totally.
Okay, good. So we've proved that M preserves identity morphisms. And the fact that M preserves composition will be very, very similar to this argument. For the sake of completeness, let's actually prove that as well. Now imagine we've got two morphisms, S and T. So S goes from X to Y, T goes from Y to Z. We've got our mx here. I'm now switching to this m of x notation instead of m subscript x. Eta x, m of y with eta y, m of z with eta z. And then we already know that we've got the m of s and m of t separately. So this is m of s, this is m of t. We know that they make the corresponding triangles commute, so these are the triangles obtained by composing. So the slanted arrow there is eta y composed with s, and here it's eta z composed with t. And we know that when I do u to m of s, it makes this first triangle commutative, and similarly, when I do u to m of t, it makes the second triangle commutative. And now let's draw in the composite of s and t. So this will be t composed with s here. And let's draw in also m applied to that composite. So m applied to t composed with s will be an arrow there. And what will that arrow do? Well, it will have its own triangle that it makes commute, right? So let's actually, not to make the picture too messy, let's draw that separately. So m of t composed with s goes from mx to mz, and it's unique morphism that makes the triangle with mx here and mz here, x here with eta x, and z with eta z, and the composite here, t composed with s.
So I think the arrow from y to my should be reversed, should not it?
Should be what, sorry?
So there's an arrow from my to y.
Yeah, that's a mistake, sorry, thanks. So what I know about m of t of s is that u of that thing makes this triangle number 3 commute. And again, this is the unique thing that makes this triangle commute. But perhaps there is another candidate that makes, I mean, just like before, perhaps we can name already a morphism that will make that triangle commute. And then we will know that that named morphism must equal to this m of that composite, because that thing is the unique such thing. And indeed, we actually want to prove that this thing equals to mt composed with ms, right? That's what it means to preserve composition. So if I draw in here mt composed with ms, will that make, and I apply u to it, right? Will that make this triangle commutative? If it does, I apply U to this thing and it makes this triangle commutative, it means that this unique morphism that makes triangle number 3 commutative is actually this one. So what I'm trying to say is that to show that M of T composed with S equals M of T composed with M of S, it is sufficient to show that I'm going to delete this part for the sake of simplicity of the diagram. It is sufficient to show that triangle number 3 commutes. So why is that? Because once we have at hand an arrow that makes this triangle commute, then by definition of the functor M, that arrow must be M applied to this morphism. So then it means that this arrow must be the other arrow. Does that make sense, Lian? If I got you lost a little bit, you can maybe tell me where you got lost. I can rewind. How about you, Alexander? Are you fine with this?
Yep, so it's the same argument actually, yeah.
It's very similar, yes. So why does triangle number 3 commute? Well, that yellow arrow there, U of that composite, U of MT composed with MS, by the fact that M is a functor, is actually equal to the composite of these two blue arrows. And then again, this commutativity conditions can be put together. So I can algebraically write this out for completeness, but it's actually maybe even nicer to follow it on the diagram. So U of M of T composed with M of S composed with eta x. Let's compute what that is. Because U is a functor, it's the same as U of M of T composed with U of M of S. And because of associativity of composition, I don't keep track of brackets. And then I am going to evaluate this composite here. So it's U of M of T composed with eta y composed with S. And now I can evaluate this one here. So the first one is by triangle number 1. This equals that by commutativity of this triangle. But now I can evaluate that by commutativity of triangle 2 to get eta z composed with T and Zurab composed with S. And that's exactly what we wanted, right? We wanted this composite here to equal that. And so the first one is exactly this part. The second one is exactly that part. That's good. Is that good, Alexander?
Yeah.
So what we get here is a functor. It's a functor going backwards. And now we can fully summarize our findings here. So well, we already summarized it earlier. So we said that when such object exists for every x, we get a functor which we'll get convinced of below. So we already got convinced of the fact that we get this functor. So this is one of the property of free objects, that it allows you to so this producing a free object out of an object gives you a functor. And going back to our example, in the case of monoid of words, it has the following interpretation. So back to the so if I've got an alphabet X, I take words over X. I got an alphabet Y, I take words over Y. Now if I take a function, a kind of translation of alphabets, every letter is mapped to another letter. Because that thing is a functor, I should get, so if this is my M of X, and this is my M of Y, here I should get some M of F. And what will M of F do? So just on an example, so this is the two categories. Here, this is the category of sets, and this is the category of monoids. And what M of F will do is that if I take a word, let's say apple, and I apply MF to it, I can actually compute what it does by knowing how it's defined, right? Remember, this M of F is defined as F of A, F of P, F of P. Sorry. But we have to make a slight distinction here. So the underlying set of the monoid of words, which we still denote by the same words, but it actually is U of M of X. X has this insertion there, the eta X, and the same on this side, eta Y. And the triangle that is commuted by this M of F is, of course, this one. But of course, this composite here, it maps a letter X. On this side, it maps to F of X. But then we view this letter F of X as a word having a single letter. So it basically doesn't really change the form of the element. So we can think of this to be the same F of X as that one. And then we can describe this to be the word consisting of the letters F of A, F of P, F of P, F of L, and F of E. So you take a word, you replace every letter with the letter in the other alphabet, and you get the resulting word. And that process is a functor, which now proved in the general case. And so since we proved it in the general case, then it also works in a special case. Now, although it's the first time we talk about free objects, we have actually seen this scenario of free objects in the definition of exponentiation. So there, the situation was the following. This is another example. In this example, both categories are the category of sets. And we have a fixed object by which we perform exponentiation. So what plays the role of the forgetful functor is taking a set S and mapping it down to s to the power x. So this is our u of s. And it will turn out that if I begin with an object, maybe I shouldn't call this x, because x will be the name for the starting object. So let me call this thing a. If I begin with an object x, the free object for this functor would actually be a cross x. And we will now confirm this property. So we draw a cross x in there, and then we evaluate the functor. So we'll have a cross x to the power a. And now I need to specify some map eta x, right? Which will have this property of freeness, in the sense that if I took another object s and I mapped it down to, and I took its kind of underlying structure, but in this case it's just s to the power a, and I have a function f from x to there, then I should have a unique function here, f bar, that makes this triangle commutative. And this morphism here will be just nothing other than, we can call it f to the power a. So what is f to the power a? Remember that a cross x to the power a is a set of functions from a to a cross x, right? So an element in here will be a function from a to a cross x, and s of a, on the other hand, is a set of functions from a to s. So I want to produce sorry, this should, my apologies here. So this should be, it's not f to the power a, but this should be f bar to the power a. So if I'm given some map f bar from a cross x to s, then I have an arrow here. This is f bar arrow, and then I can compose these two arrows to get an element of s to the power a. Another way of thinking of this is that this is our home set, a cross x. This is our home set, as, and this is our home map, af, which is just, sorry, af bar, which is just composing with f bar. So I'm claiming now that for every f there is unique f bar, such that the triangle commutes. If this is true, then this will be proving that we have a free object, right? By definition, a free object relative to this functor. Okay, so let's write down what it means for this to commute, and we will see that it will force f bar to be unique indeed. So I'm going to keep a general f bar, and I'm just going to write down what it means for this to commute. So first of all, I need to describe, I haven't yet described what eta x is. Eta x will map x to, it needs to map it to a function from a to a cross x, right? It needs to be a function from a to a cross x. So I need to decide where to map a, small a. What do you think would be a natural choice here, Alexander? I see that Liam stepped
A
out
and
for a while. Sorry to interrupt. Maybe that's also why he didn't
A
answer.
and X maybe.
Yes, AX.
Okay.
So eta x will be defined like this. It's actually, I should write this slightly differently, right? So x maps to that by eta capital X. Okay. So now we want to analyze what is commutativity of this triangle. Let me draw it separately here. And now I know if I begin with a small element x, I know where it will map to. It will map to that mapping of A to A comma x. And then I apply f bar to the power a. But remember that just composes the thing with f bar. So I've got this mapping a going to a to the, a comma x, and now I need to compose that with f bar, which will lend me in s. So it will map this mapping into the mapping of a going to where, Alexander? What happens when I compose this mapping with the f bar mapping? Got a maps to a comma x, and now I need to compose that with f bar. I will get
So
simply,
that,
yeah.
Okay, yeah.
I will get this, right?
Yeah.
Okay, so we know exactly what will happen with x when I chase it around the triangle. X will get mapped to the mapping of a to f bar of ax. Yeah. And that has to be the same as where f takes x. So, well, where does f take x? F takes it to f of x is some mapping from a to x, right? It maps small a where? It maps small a to f of x applied to that small a, right?
Right.
These two mappings have to be the same mapping. Doesn't that mean that f bar of ax must be equal to f of x applied to a?
Yeah.
Which shows my uniqueness and existence as well.
All right.
So that's how
So we have proven that this operation is a Frey functor, or
yes.
okay.
Yeah. So we talked earlier, so in the context of structures where u is called the underlying, the forgetful functor, then the other functor which we construct can be called the free functor. In this case, it was our m. But now this one is a bit different from the example of structures. You don't want to really think of this construct, or rather, you don't want to think of this construct as an underlying set of S, right? We will never think of it like that. But yet it's an example of the same phenomenon. Okay, so what is that phenomenon? Let's now formalize this idea. So by formalizing this idea, we will come to another way of defining a junction, which is an equivalent way to the one we encountered before on the example of exponentiation. A functor u from m to s is said to be a right adjoint when for every object X in S, the comma category X comma U as an initial object. The corresponding functor which we constructed earlier, going from S to M, which maps is constructed as above. So it maps every object to the object part of the of that initial object in the comma category, and on morphisms is defined using those triangles that we spoke earlier. So this corresponding functor is called a left adjoint to U. When M and S are categories of mathematical structures, let me give a name to this functor, the corresponding functor going backwards. Let me call this F. It's because of free, we'll call it F. We didn't call it F thus far. We should have. We were calling it M, but I want to now call it F. When MS are categories of mathematical structures, and U is the, well, N, because it could be several, underlying set functor, underlying structure functor, F is called the free structure functor. Okay, two remarks to be made here. One is that this definition seems to be very asymmetric, because what we do with U is very different to what we do with F. I mean, we begin with a functor and then we construct F out of U. But it turns out that we can actually have done everything the other way around just by dualizing this whole story. Eta will dualize, this direction will swap. That's why sometimes I was mistakenly writing the direction of eta opposite way. It will then be called epsilon. And so there will be an equivalent dual definition of this definition. So if I dualize this definition by taking duals of every category, I will actually get definition where right adjoint will become left adjoint and left adjoint will become right adjoint. There is also a symmetric definition of adjunction, which is the one that we gave during the definition of exponentiation, where both F, the left adjoint and right adjoint, had similar roles in the definition. It was obvious to see how they have dual roles. So that's one remark which we're not going to explore now. Another remark that we are going to look into now is, what about examples where the underlying structure is not just a set, that itself is a structure? And specifically, I want to look at the construction of polynomial ring. Do you know what the polynomial ring is, Alexander?
Yeah, I do.
So we've got this interesting functor from sets to rings, which picks a set X and assigns to it the ring of polynomials. Let me write it this way. where the variables in each polynomial are elements of x. So elements of this are sums where you've got some coefficient, which is an integer, and then you multiply that by some word of elements in x. So this goes from I to n. N is an actual number. Ci is an integer, and wi is element of the category of words. Sorry, of the monoid of words over x. This functor is actually the free functor for the underlying set functor, going from the category of rings to the category of sets. So we've got our U1, F1. The reason why I call them 1 is because I'm going to have more of these now. Here, one should actually define what one means by this, right? For instance, if you swap the order of summands, it's meant to be the same sum, not a different one. Then also, if you have terms that are same, then you want to group them under one term. All the standard manipulations that this sum and product notation would allow you to do are allowed to get equality of two such expressions. So I'm not going into this in detail now. What I want to say is that this adjunction actually splits into two adjunctions, which is kind of already visible here, because we seem to first need to construct words before we construct the polynomials. Of course, these are just polynomials in the variables from the set x, right? So there is this intermediate category monoids, and which has its own underlying set functor, and own free functor. And this is the usual one we already worked with today. This will be the monoid of words functor. But there is something connecting these two as well. You can start with a monoid. Well, first of all, there is an underlying functor here, right? This is the functor that forgets the addition in a ring. You know what a ring is, right, Alexander?
Yep, of course.
So yeah, a ring has a whole a set with two operations, basically. I'm going to use a shortcut here. I'm just going to write it like this. It would be nicer to list all the entities involved, including the identity elements. But just for simplicity, I'm going to write it like that. And then what U3 does, it forgets multiplication. Sorry, it forgets addition. It just skips the multiplication. Which by definition of a ring, if it's a unitary ring, and here we do assume this is the category of rings with unit. So there is an element that's a multiplicative identity element. So we get a forgetful functor from rings to monoids. And just like in most cases forgetful functors do, this one also has a left adjoint. And what this left adjoint does, it constructs free ring over a monoid. Now, what does that mean? So if I have a monoid M, right? In my free ring, I want to now be able to add elements in a monoid, right? So I want to maybe form expressions like this. But in a ring, I should also be able to multiply them, yeah? But the monoid already has multiplication in it. And because of that, multiplication shouldn't be the new multiplication, it should be the one that comes from M. So if I want to multiply two sums, like for instance this, and let me say, if I want to multiply, let's say, x with y plus z, instead of that being a new term of its own, well, in this case, because of distributivity law, I would want that to be the same as this, of course. But now, this product and that product will not be a new product. It will be the same product that I already have in the monoid M. So maybe we distinguish the two products by writing dot bar for the ring product. What I'm trying to say is that by distributivity, the ring product should behave like this, but then what I'm saying is that the ring product should match with the monoid product. So it's a free construction, but only partially free, because we are keeping the monoid structure. We're not adding the monoid structure. We're only adding the additive group structure. Does that make sense, Alexander?
Yeah, it seems very naturally.
And then it turns out that because this underlying set functor is a composite of these two, also the free functor will be a composite of these two. That's actually a general theorem, that if you have two right adjoints, you take their left adjoints, you compose them, that composite will be a left adjoint of the composite of right adjoints. It's one of the nice properties of a junction. So this is just an example of where we have this relative freeness, namely this specific one between rings and monoids, which is a useful stepping stone for building the polynomial ring, if we already have this construction for the monoid of words. There is a video of mine about the junctions from last year. I will probably recommend everyone to look at that video as well. The concept of an adjunction has several different equivalent definitions, and understanding these definitions and their equivalents and working it out by hand is a necessary condition if you want to claim that you understand category theory. So the two big ideas to be understood before you will feel comfortable in category theory are adjunctions and Yoneda embedding. Yoneda embedding is something that links up with generalized elements. We will still come back to that. If I had to give complete lectures on adjunctions with all of its aspects to the point that I want, that I'm saying that the understanding should be, if you want to be comfortable with category theory, it would probably take 10 lectures. So it's a big topic, because you want to understand not just the equivalent definitions, but you also then want to understand examples and build by hand these free functors. The thing is that one thing is to define what it means. Where are we now? One thing is to define what it means that something is a right adjoint functor. Another thing is to prove that in concrete cases it actually is a right adjoint functor. And we kind of sketched the proof of that in the case of monoids. We proved that the forgetful functor from monoids to sets is a right adjoint functor by this discussion with words. And we also sketched the proof in the case where the functor was the exponentiation functor. But these are just two examples among a sea of many, many other examples, most of which are very important in mathematics. So the topic of adjunctions is a 10-lecture course of its own. The topic of Yoneda embedding would be another at least 5-lecture course, because Well, I mean, if we count the fact that we already know what a functor is, we still need to define natural transformations for this, but also for this actually to recover those etas. Those etas will turn out to be natural transformations, as I indicated before. So we need that concept in both cases. So both of these rely on the concepts of category, functor, natural transformation, and once one knows these three concepts, after that, each of these topics would be 10 lecture material. But it's much better to unpack these topics yourself, much more fun than listening to somebody else do that. So we are touching, in these lectures, we are touching kind of on the surface, these topics, just to give you an intuition and possibly for you to decide whether you're interested or not to explore the topics further. Okay, any questions, Alexander or Lian?
I have a question actually.
Yes.
So, as far as I remember, an example of a free object when we consider categories of, I think, sets and topological spaces are like discrete topologies.
Yeah.
But there is, as far as I remember, as an opposite example, so to say, as an indiscrete topology. So is there like some dual notion of free object that gives us the indiscrete topology?
Exactly. And that dual notion is exactly what I referred to earlier when I spoke of dualizing the definition that we did. So let's actually sketch how that would look like. So the free construction was defined by the following picture. So we had X, we had MX, but I'm not now going to call it FX. Then we had UFX and eta X. And so these were the two categories here and there. And then we said that if I have another object up there, let's call this object maybe even M. And then we take UM, and I have a morphism F. Then there must exist unique F bar, such that U F bar makes this triangle commutative. Now I could dualize the whole picture. I again start with X. This time my functor still goes down from top to bottom, but my eta will now be reversed, so this will now then become epsilon. And so what I will have here is still U of, I don't want to call it U anymore. That U will rather play the role of F. So this will be, let me call it, maybe, you know what, I'm going to call this M the way I used to before, so I'm use the letter F for the second one. And then I'm going to call it M prime. So F of G of X, so G of X will be something up there. And the condition will be that if I have another what do I call it? I may still call it M prime, this one. If I've got another M prime there, then and I have any morphism here, G, then there exists unique morphism that way, G bar, such that we've got F of G bar, making this triangle commutative. Given the first case, this was an initial object in the comma category X, comma U. In the second case, it will be a terminal object in the category F, comma X. Now you see the roles have been swapped here as well. when our functor is the underlying set functor, and when the top category is the category of topological spaces, and the bottom category is the category of sets, so top and set, and this being, so our U in this case is the same as the F. Then M X will be X with certain topology. Now, you see that topology needs to be such that it turns any function going out of X into a continuous function, right?
And so in discrete.
Yeah, so it will be topology where everything is open.
Discrete, yes, sir.
Yeah. Yeah, sorry, it's discrete because we want everything to be open, because we want any function to be turned into a continuous function. And in fact, the set will be the same X. It will not add, unlike in a monoid where we have to add new elements, because there is no operation in topology. Basically, we don't add any more points to the set. We keep the same set, but we just have to decide what the open sets are. And so this will be all possible subsets. So it will basically power set of X. All possible subsets are open. Why so? Because I mean, I could have taken this topological space to be the one where everything is open, and then continuity of this would have forced those to be open as well in there. So this will be going back one way, and this other dual way of going back, this is the opposite. I want any function from any other space into my set to now become continuous. And remember, continuity means that inverse image of open is open. So what if M prime has very few open sets? If M prime has very few open sets, I still want G to be continuous. Right? So I need to have in X as few open sets as possible. And so the fewest possible ones we can have is the indiscrete one, right? You agree with that?
Yep, now I see how it's symmetric.
Yeah. But what is interesting is that in the first case, matches our original setup. So in the first case, U is right adjoint, and this M is left adjoint. Whereas in the second case, it will be the other way around. Namely, G will be right adjoint, and F will be left adjoint, where the U and the F are actually the same thing. Yeah? So this functor is both a left adjoint and a right adjoint, but it's left adjoint and right adjoint to different functors. It's right adjoint to this discrete topology functor, and it's left adjoint to this indiscrete topology functor. In general,
so by this functor, you mean just forgetful functor from top to set?
Yes, yes. And in general, one can prove that when U is right adjoint and M is left adjoint, U op will be left adjoint. We dualize the functor. And M op will be right adjoint. So this kind of hints on what same idea I said earlier, where I said that there was asymmetry in the way we defined a junction today. But then I said that, in fact, if we dualize, the roles will swap around. And then there is also a symmetric definition of a junction, which we already pointed out before, which was natural isomorphism between HOM f x y and HOM x uy. And when we say natural, it means it's natural, that this mapping is a natural transformation of phi. This phi is specifically now drawn for components x and y. So we first need to turn the left-hand side into a functor, the right-hand side into a functor, and this, which we did last time. And then this will be a natural transformation, which is an isomorphism between those functors. And this is the symmetric definition of a junction. And the one we gave today is the asymmetric one, but all of them are linked, and these links are the things that one needs to clarify if one wants to understand the junction as well.